Have you ever wondered what makes the flicker of a neon sign, the sterilization of surfaces, the efficiency of modern microchips, or even the scientific justifications for seemingly impossible technologies in many sci-fi movies? The answer lies in an extraordinary state of matter: plasma. But not just any plasma. Unlike the searing hot plasma in stars, low-temperature plasmas are way cooler, often near ambient conditions. When an electric field is applied to a gas, the supplied electrons collide with the gas-heavier species, ionizing them. The resulting ejected electrons trigger a cascade effect of further collisions and ionization. Despite the presence of a high-energy electron population, with temperatures reaching 100,000 kelvins, the overall temperature and volume of the plasma is primarily determined by the denser neutral species, which can remain at a low temperature, hence the term low-temperature plasma. In the plasma soup, this high electron temperature promotes a higher collision rate, accelerating reactions and enabling the creation of new species, making the entire process more effective than traditional thermal methods. Inside the plasma, reaction mechanisms unfold like intricate dances between particles, driven by a cascade of interactions. Coupled with the higher collision rates induced by the plasma's energetic electrons, these reactions create a rich environment for chemical transformation and efficiency. Molecules collide, exchange energy, and break apart into fragments, creating entirely new species. To actually start making predictions, we need to understand the rate at which these reactions occur. This is where the rate coefficient comes in. It tells us how fast a reaction happens, and we use it to calculate how much of a species we will get after some time. Usually, most of these values can be found in the literature. However, rate coefficients of reactions involving electrons can be calculated using two critical pieces of information: cross-sections, which essentially tell us the likelihood of a reaction, and the electron energy distribution function, or EEDF for short. The EEDF describes how the electrons in the plasma are distributed across different energy levels. To find it, we often solve the electron-Boltzmann equation. One approach is the two-term approximation, which simplifies the process and gives us a reliable estimate of the EEDF. Once we know the rate coefficients, we can simulate the plasma. By solving a system of rate equations, we track how the densities of ions, electrons, and neutrals evolve over time. These simulations allow us to predict and optimize plasma-driven processes with precision. Low-temperature plasmas are more than just a scientific curiosity. From enabling green chemistry to powering the next generation of devices, these plasmas hold the key to a brighter, more efficient future. And it all begins with understanding their inner workings, one reaction at a time.